Okay, so had a bit of a technical difficulty, but we're back. So the first thing we need to do when we're going to construct now I'm going to talk about, so what we know is this. If we survey all those situations and we find a situation where it's where the sentence is, if the sentence is true on all the rows of the truth table, it's true in all situations, and so it is a tautology. And if there's a row of the truth table on which it's false, then we know there's a situation in which the sentence is false, or there's a possible situation in which the sentence is false, and therefore the sentence is not a tautology. So what we need to do is figure out how to make the truth tables, how to construct them, and then how to calculate the truth value of a sentence. So first I'm going to talk about constructing them, and then I'm going to talk about the truth value calculation, and then I'll give you some examples in the module. So we have to make sure that we survey all of the different possible combinations of truth values. So if a sentence has n many different atomic letters, and these are kinds of letters, so P or Q or R has 3, whereas P or Q has 2, then the table has 2 to the n rows. So if it has one sentence letter, it has 2 rows. If it has 2 sentence letters, it has 4 rows. If it has 3 sentence letters, it has 8 rows, and so on. So we got to set up the table to make sure we list all of the possible combinations. So the way you can do it is you can start in the right row, the row that's in going to be, you're going to have all the sentence letters, and then you're going to have columns for each of the sentence letters, and then a column for the whole sentence. And so you want to start in the rightmost of the sentence letter columns, and you alternate to be true, false, true, false, true, false every other row. In the next row to the left, you double the alternation, so it'll be true, true, false, false, true, true, false, false. And if there's a third row, then it'll be true, 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 false, 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 true, 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 false, 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 false. And you'll just keep going like that, but you won't need to do more than that. So we can see an example of how to set up the truth tables if we actually go into the truth table module. So let's take a look at this first problem, 2, 0, 0, 0. So we have to ask what are the sentence letters, and so we'll list them. They're P, and we put a period between them, and then we say Q. And so we have to say, how many rows does that mean we need? Well, that's 2 sentence letters, and it's always 2 to the n, and so n is 2, so 2 to the 2, and 2 to the 2 is 4. So we say, okay, we've done that. We move on. So now it sort of begins to, now we have to figure out what we have to fill these in. So following the pattern, we're going to make this going to be true, false, true, false. Then we double alternation, so this is true. And then these are both false because we're doubling the alternation. And this gives us all the possible combinations of truth values that P and Q might have. So we've done this. And so now we then need to actually figure out whether or not this thing is a tautology. To do that, we're going to actually go and look at some demo problems. So here we have the sentence, the biconditional sentence, if not P then Q, if and only if P or Q. So we're going to have to give an answer here. So let's say we said yes, which in fact it is, and we checked it. Just incomplete. Why? Well, because we need to show that this thing is true in every situation no matter what. So we need to show that it's true if both P and Q are true. It's true if P is true and Q is false. It's true if P is false and Q is true. And it's false if they're both false. And we haven't done any of that. So what we do to show that it is true is we click on the question mark. And now this tree pops up, right? And this is the tree. And what we know is that the truth values go up the tree. So we know that if we look at P or Q, we know that its truth values are determined by the truth values of P or Q. And in particular, we know that if both disjuncts are true, then the whole disjunction is true. Now, if we look over here, we can do something subtle. This is a conditional. It has a true consequent. And a conditional with a true consequent is true whatever the truth value of the antecedent. So we can click there and say true without filling this in. It doesn't matter what truth value not P has. In fact, it's false, but it doesn't matter. this thing is true, given that its consequence is true, whatever truth value not p has. So we don't have to fill out the entire tree. What we have to do is get a truth value here. And this is a biconditional, both of whose components are true, so it's true. So we'll click OK, and now this becomes true. So we need to just repeat this. So we say, OK, disjunction, p is true, the disjunction is true. Now here, is this true or false? Well, the consequent is false. So let's say we said that it's true. Well, now we have an error, right? Because there are conditionals that have false consequents that are false. So this by itself, the truth values we have filled in, don't suffice to determine the truth value of this whole thing. We need to say that if p is true, then not p is false. And now we have a conditional with a false antecedent and a false consequent, and we know that such a conditional is true. And so now so when that red goes on there, it could mean you put in the wrong truth value, but it could also mean that the truth values you've entered lower in the tree aren't sufficient to determine that the thing is true. Maybe you got the truth value right, but you haven't proved that that's the truth value. But now we have these are both true, and so we can say true. So again, to see a problem of this kind, right, if I just say, oh, true, well, that's correct, it is true. Note if I say false, there's no way of telling, and that's the point. If you put in a value that's not fully determined by the values you've entered in, then it will give you an error message. So in fact, it's going to be true. Why? Well, Q is true, so this disjunction is true. Q is true, so the conditional is true, so the whole thing is true. And finally, if we go over here, P or Q, both false. If P is false, then not P is true. So we have true antecedent, false consequent. We have a false conditional. They're both false. The whole thing is true because the biconditional says they have to have the same truth value. So we've proved that indeed it is a tautology. And if we check, then we get a correct answer. So that's what we do. And we'll just do one more to see, just get a handle on this. So here we have not P or Q if and only if P or Q. Oh no, that's not what we want. We want this. We want if P then Q, if and only if P or Q. So let's say we're not sure whether or not it's a tautology. So let's go to the first one. P or Q, both disjuncts are true, the whole thing is true. True antecedent, true consequent, true conditional, biconditional with true components, that's a true biconditional. Okay. Conditional with true antecedent and a false consequent, that's a false conditional. Disjunction with a true disjunct, that's a true disjunction. So now we have one component of the biconditional is false, the other is true. They have different truth values. That means it's false. That means this is not a tautology. So let's say we say no, right? We found a row on which it's false. We check it, it says incomplete. We must check a row in which all premises are true and the conclusion is false. Or we must check a row in which the thing is not a tautology, in which it's false. So we check there. And then we say check, and we get it correct. And we don't have to fill these in. Just like you don't necessarily need to fill in all the points in the tree, as we saw in the previous example, because in some cases it doesn't matter. You would get the same answer however those nodes were filled in. Same thing here. If these are false, that's fine. If they're true, it's fine. Either way, our answer that the formula is not a tautology is correct because it's false in this situation. And that's all we need to show. So that's the truth table module. I think it's pretty straightforward. Yeah, but again, questions? Let me know. The remainder of the videos in this section will be some symbolization topics.